Okay, before we continue, I want to pause and talk a little bit about logarithms, and in particular, why we see and use logarithms so often in kind of probability and statistics and probabilistic machine learning. And in the process, define a couple of things that are going to be important when it comes to, for example, logistic regression. So our first question is, why do we use logarithms so often in probabilistic models? And then usually it comes in the context of log likelihood. So when we're writing down a likelihood, remember a likelihood is the probability of some data given some particular model. Let's say we have three observations which have probability P1, P2, and P3 respectively. So one thing that's a bit counterintuitive is that we're used to adding things together. For example, if we get a new data point, we would think of adding on something to our likelihood, but instead we multiply on. So one way to fix that is if instead we take the log of the likelihood, then each time we see a new observation, we add something to our log likelihood instead of when we're just representing the likelihood, we're multiplying it. So I think handling log likelihoods is a bit more intuitive, again, because we are adding things rather than multiplying them. And by the way, we almost always use the negative log likelihood. The reason for that is that these logs, notice that P probabilities are always less than 1, so their logs are always negative. So since it's maybe more intuitive to deal with positive numbers than negative numbers all the time, we usually use the negative of the log likelihood. So you can think of this negative log likelihood as like a unlikelihood score, and score in the sense that it's something kind of intuitive, that the more data we get that shows that something is unlikely, then the higher the score will be. Okay, perhaps that was a bit kind of wishy-washy. So let's talk about a kind of more concrete reason that it's important to use logs. And that is when it comes to numerical precision in dealing with floating point numbers. So to understand this, we need to remember how floating point numbers are represented in a computer. And that is like this. We have two parts. There's some number, which is represented as an integer with some number of bits. That's called the significand. And then there's a second number, which is again an integer. And the way you get the final number is you take the first number times 10 to the power of the second number. And both can potentially be negative. There's 1 bit reserved for each one being negative. And in a modern double precision floating point number, we have 11 bits for the exponent. 1 bit each is used for the sign. Each one can be either positive or negative. So we have 52 bits of precision and 10 bits of precision here. So that is, we can handle an exponent between 2 to the power of 10, that's about 1,000, and 2 to the negative 10, which seems like a huge range of exponents. And it is when it comes to sort of normal numbers that we see from day to day. But when it comes to probabilities, and specifically likelihoods, well, what is the likelihood of seeing a given sequence of 2,000 coin flips? That probability is 2 to the power of 2,000. Now, 2,000 is a lot of coin flips, but it's not a lot when it comes to most of kind of the data applications we have, where we have often, tens of thousands or millions of examples, and we want a likelihood of all of those examples together. So we'll get probabilities that are much less than 2 to the power of negative 2,000, or negative 1,000 is the lowest the floating point number can handle. And if we do that, we'll get what's called floating point underflow, where this number gets to be less than 10 to the negative 2 to the 10, and the floating point number will it'll just call itself 0. That's what the computer does to handle that case. So you'll run into this very quickly if you're ever doing any kind of machine learning application where you're dealing with likelihoods. You'll very quickly run into floating point underflow, where all of your floating point numbers will turn to 0 and it'll mess up all of your analysis. So what we do instead is, instead of storing the number like this, instead we store its log. And the log likelihood won't go anything close to those extremes. So that'll still work. Okay, let's give another reason that we use logs all over the place. And that's because it's very often easier to do all of our kind of mathematical derivation when we're using log likelihood rather than likelihood itself. So for one example, let's look at the case where we have, we want to find the maximum posterior. Well, we've already seen this. The posterior looks something like this. And to take the derivative, we do d over d theta of this whole thing. Now, I don't know about you, but this looks hard to take the derivative of because we have a product between two things, and each one is probably going to be complicated. Now, instead, what if instead we maximize the log likelihood instead of the likelihood itself? Now, logarithm is monotonic, meaning if we increase the likelihood, we also increase the log likelihood. So the maximum of the log likelihood is always going to be exactly the same as the maximum of the likelihood itself. Then we get an expression like this. Which we can divide then we get an expression that looks like this. We have the derivative of the log of this posterior probability, which breaks into these two chunks, the first term plus the second term. And we're very familiar with how to take the derivative of sums. Forgot to put the derivative in here. And in particular, we can take the derivative of each side separately. By the way, you can absolutely do this derivative and you'll get the same answer. It's just tends to be a lot harder. One note about the base of the logarithms we're using. So you'll note that when I write log of x like this, I haven't been writing what the actual base of the logarithm we're using is. In practice, you'll see a couple different bases. Log base 10, base 2, or base e are the most common. When we write log base e, that's the same as writing ln, the natural log. It doesn't matter in practice which base you use very much. We could do everything we're doing with a different base 5 if we really wanted to. The reason being that logs of different bases differ just by a constant factor. And specifically, that constant factor is 1 over log b of a. That's what that constant factor is. In the class, we're going to exclusively use pretty much log of e. That is, we're using the natural log, but we're going to write it using the normal log like this. Just I think writing ln everywhere is a bit cumbersome, and that's what the textbook uses. Okay, so just be aware of that. When we say log, we always mean log base e. Okay, so those are kind of some practical reasons for why we use log likelihood all over the place in probabilistic machine learning. But I think there's kind of a deeper conceptual reason. I, at least personally, find that sort of nothing in probabilistic machine learning makes sense except in the context of log likelihoods. So let me give an example. So recall that in logistic regression, we use the logistic function, which is often written like this: 1 over 1 plus e to the minus a, where a is our score. And we write the logistic function itself as sigma of a. So, this is fine, and this correctly defines the logistic function, but it kind of doesn't give a lot of intuition for why this function and why not some other function. So I think maybe a way to understand why this function makes sense more than anything else is as follows. So let's say we have two things that we want, that we have scores for, a score for kind of how likely we think this thing is, A and B. So recall that when we're thinking about probabilities and we have kind of intuitive scores, then we almost never want to put that score as the probability. We want to put e to the power of that score. So now we have these two options with probability e to the a and e to the b. But of course, these probably don't add up to 1. So to normalize it, if we want the probability of a, that's e to the a divided by, you take those two things and you sum them up. And in fact, what I just wrote here, this is just another way of writing the logistic function. Specifically, this is the logistic function of a minus b. If you you can if you want, you can actually do the algebra to figure out how we got here. Basically, we divide top and bottom by e to the a. So hopefully that gives a little bit more intuition about why we see the logistic function everywhere. It's kind of a natural consequence of this idea that if we have an intuitive score, or in practice, a score that comes from our machine learning model, either logistic regression, that would just be a linear function of our inputs, or very often we have a neural network that outputs some score, then we put that through a logistic function to get the probability of our label. So the reason the logistic function comes up all over the place is this fact that it's kind of a natural consequence of this idea that if you have a score and you want a probability, you want to take that score as an exponent. So again, what I showed here, this is exactly the same. It's exactly the same mathematically. I'm just trying to grant a little bit of intuition for why this makes sense. Okay, now let's do that same thing for a Gaussian distribution. So for a Gaussian distribution, let's for now start with a Gaussian distribution of mean 0 and standard deviation 1. So with a Gaussian distribution, the main property of this distribution is that the distance from 0, the probability gets more and more unlikely proportional to the distance from 0 squared. So it's going to be x squared negative. That's kind of our unlikelihood score. Then to get the probability, or in this case, the probability density, we take e to the power of that unlikelihood score. So this thing is our Gaussian distribution. Everything else just comes along from that. So first thing, we need some 1 over z that makes this thing integrate to 1, because this thing as it is wouldn't integrate to 1. That turns out to be 1 over the square root of 2 pi. So it has this kind of scary looking constant factor out in front of it. That's where that comes from. And then where we get the other parts of the Gaussian distribution is so that we can pick a specific mean and variance. So that's why we see e to the power of negative x minus mu squared divided by 2 sigma. And then once we add that, we also have to add sigma squared here in our constant factor. Okay, so again, this is the same probability density function I showed you. I just wanted to give you some intuition for why you see Gaussian distributions everywhere. Gaussian distribution is really just kind of the probabilistic form of squared error. You take your error, you square it, then you have to do some constant factor stuff. And that's where the Gaussian distribution comes from. Okay, so that's all I'm going to talk about when it comes to logarithms. I hope that gives you a little bit of kind of intuition for why we use logarithms, and hopefully this makes sort of these standard distributions we use, like the Gaussian distribution and like the logistic function that transforms the score from a machine learning model into a probability. I hope that gives you a little bit of intuition for why we use these distributions rather than something else.